Okay, great. So let's continue. So we had been talking about the quadratic form for the graph, and in particular, one thing this involves is choosing a random edge and looking at a function value at the endpoints of the edge. So we've been talking about choosing a uniformly random edge. We should probably also talking about choosing a random vertex too. So should we just think about choosing vertices also uniformly at random? No. So this is actually one place where the fact that we're potentially working with an irregular graph makes a difference. If you're just working with a regular graph, then when you're thinking about choosing a random vertex, you should just choose a uniformly random vertex. But if you don't have a regular graph, then it's important to choose a special probability distribution on vertices, which is what we'll talk about now. Okay, so how to choose a random vertex? Let's think about this. Okay, so I'm actually going to define the way to choose a random vertex in a slightly funny way. I'm going to define it as follows. So here's a process for choosing a random vertex in the right way. Start by choosing a uniformly random edge. Well, let's call it choose a uniformly random edge, UV. Okay, and then just forget about V. Just output U. Now actually, as we'll see later, you could also say forget about U and just output V. It would be the exact same thing. Okay, so this is a funny way to draw a vertex at random. And if you think about it for a moment, it's sort of biased towards choosing vertices with very high degree because they touch the most edges. Let's call this distribution pi. So pi is going to represent a probability distribution on vertices. And if we think about it, let's say for this graph here, with 5 vertices and 5 edges, this is an irregular graph, notice. And what are the probabilities with which each of the vertices is chosen under this pi for this graph? Well, if you notice, we'll choose a random one of the 5 edges. It doesn't really matter too much which one. And then we choose, let's say, the first vertex in that edge. So remember, when we draw a uniformly random edge, we think of it as being directed. So if we choose a random edge, perhaps we choose this edge at random. There's a 50-50 chance that we're doing the version that goes from the center vertex to the outside vertex, and a 50-50 chance we're doing the directed edge that goes from the outside vertex to the center vertex. Okay, and what that means is under pi, pi of the center vertex is a half. And all of the other vertices have the remaining probability, and so each of them by symmetry has, let's call it pi of a leaf, is 1/10. Okay, so you can see this is definitely not the uniform distribution of vertices. The central vertex actually has half the probability mass by virtue of the fact that it is a very high degree. Okay, so pi is a probability distribution that is biased towards the vertices of high degree. And in fact, it's very easy to see, this is almost immediate to compute, that this probability mass pi of a vertex u is directly proportional to the degree. Okay, so pi u is proportional to the degree. And therefore, we can exactly say what it is. Pi u is, in fact, equal exactly to the degree of the vertex u, divided by, not the number of edges, but twice the number of edges. Okay, and again, that's because, this is a bit messy, let me rewrite it. Really, when we think of drawing a uniformly random edge, we think of drawing a uniformly random directed edge, and there are 2 times cardinality of E directed edges. Okay, and then the probability that its initial vertex, the one we select here as u, is precisely the degree of u. Okay, so as I mentioned, the way to think about this is that this gives a weight to each vertex, which is somehow a measure of importance for the vertex. And another key fact that we can see from, let's say, this formula here, is that if it's a regular graph, if G is regular, then pi is just the uniform distribution. Okay, so if G is regular, then pi is just the uniform distribution on V. Okay, and that's one main reason why it's nice the first few times you learn about this stuff to just imagine that the graph is regular, and then the natural probability distribution you have on vertices is just the uniform distribution. Okay, there's one more fact that we need to kind of always keep in mind about this, or to remember about this nice probability distribution pi on the vertices, and that's the following. Suppose we do the following kind of experiment. First, we draw a random vertex u from this probability distribution pi, which I've just finished defining. And now, having drawn u, suppose we let v be a uniformly random neighbor of u. Okay, and I'll actually typically write this as v tilde u. Now we think of this as a way of choosing a pair of vertices, u and v, first drawing u from the special distribution pi, and then taking a uniformly random neighbor from it. The fact is that this process is equivalent to our old friend drawing a uniformly random edge, uv. Okay, it takes a little bit of thought to see why that's true. Maybe one way to understand it is to look at this formula here. So first u is chosen in this little experiment, and the probability that u is chosen is degree of u times 2, divided by 2 times the number of edges. And then condition on u, let's say condition on getting to some vertex u, we choose a uniformly random neighbor of u. Okay, how many neighbors does it have? It has degree of u, many neighbors. Okay, and so each of them, v1, v2, v3 here, is chosen with equal probability, and that equal probability is 1 over the degree of u. So the probability that we'll choose u and v together is this quantity here, the degree of u over 2 times the number of undirected edges in the graph, times, I'll write it over here, probability of choosing u and v together is this quantity times 1 over the degree of u. Okay, and you see then these two things cancel out, and we get the probability of choosing a particular directed edge, u comma v, together, is in fact this quantity 1 over 2 times the number of undirected edges, or 1 over the number of directed edges. Okay, so we indeed see that the combination of these two steps produces a uniformly random directed edge. Okay, and so this is showing another way in which this special probability distribution pi on vertices is sort of compatible with the uniform distribution on edges. Now, if you think about it, what this means is if we draw u from pi and we let v be a uniformly random neighbor, then u comma v is a uniformly random directed edge. And therefore, if we were to do this and then output v, well, then v can be thought of as being drawn by first choosing a directed edge and then outputting the terminus of that directed edge. And as I mentioned before, that's really the same thing as the probability distribution that defined pi. And therefore, and the reason for that is in the definition of pi, the probability of drawing the directed edge uv is the same as the probability of drawing the directed edge vu. They're both equally likely. So either endpoint of an undirected edge is equally likely to be the terminus or the initial point. Okay, and that's why this probability distribution up here, had we chosen v instead, it would have been the same probability distribution pi. Well, going back here, we see that effectively doing this probability distribution to gives us a uniformly random edge, and then if we output its terminus, we get v. So all of which is to say, this is a key property. V, output by this little procedure in this box, is also distributed according to pi. It's kind of messy. I'll rewrite that a little bit. Okay. So this actually leads us to thinking about what's called the standard random walk on our fixed undirected graph G. The standard random walk on a fixed undirected graph G is simply the one where when you start at a vertex, you choose one of its neighbors uniformly at random and you go to that neighbor. And then you choose one of that vertice's neighbors uniformly at random and you go to that neighbor. Okay, you keep going, walking throughout the graph from vertex to vertex and always choosing a uniformly random neighbor of your current location as the place you go to next. And one thing that we've just discovered is that if your initial point, your initial vertex, is not fixed, but it's random, and your initial random vertex is not, let's say, uniformly random, but is drawn according to the special distribution pi, then you have a very nice property. If the initial vertex is drawn according to pi, and you take one step, the overall distribution of your second vertex is also pi. That's the v here. And therefore, if you were to take another random step, the overall distribution in the whole random experiment of your third vertex is also pi. And if you do yet another step, the overall distribution of your fourth vertex is also pi. So let me summarize this a little bit. As a corollary of all these discussions, fix some number t, a natural number, sort of the number of steps you're going to make in a random walk. So in your mind, think of t as like 17 or something. And now draw an initial vertex u according to our special probability distribution pi, which again, for a regular graph is just the uniform distribution, but in general it's proportional to the degree. And now imagine you do the standard random walk, as I described, starting from u and going for t steps. Okay, so you start at a vertex u, you step randomly to a random neighbor, you step, keep doing that, and you step t times. So I'll write like this, t. And you look at the final vertex v that you end up at. Then, in this overall experiment, v's distribution is also pi. And that's the reason that the special distribution pi is called the invariant distribution for the random walk on your graph, or sometimes the stationary distribution. I slightly prefer invariant though. Okay, it's the invariant distribution for the standard random walk on the graph, and it's so named because if you choose an initial vertex that's according to this distribution, then for all subsequent steps of your walk, the distribution of your position is invariant. It's always pi. You draw from pi, you take a random walk of 17 steps, you look at where you end up. It's always, the location where you end up is always, has probability proportional to, the probability of being in any one place is proportional to the degree of that place. Okay, so that's a beautiful property of this special distribution on vertices, the invariant distribution. But now let's look at another case, maybe the slightly less beautiful case, where you have some random vertex u0, which is not random. I didn't choose it from pi, I chose it from some worst case distribution. Maybe my adversary chose u0. And now I do a standard random walk from this vertex. Okay, so maybe I chose some obscure vertex that has degree 1 to be my u0, but then I start doing my random walk. Okay, so let's say we now do a random walk starting from u of t steps. I forgot to mention this a while ago, but you can see now the reason why we disallowed vertices of degree 0. Because if you have a vertex of degree 0, and you imagine starting there, then there's no way to do a random walk from it. It no longer makes sense. And another reason, if you recall the, well, not another reason, but if you recall the definition of the stationary distribution, it gives 0 probability to isolated vertices because they have degree 0, so it's kind of unnatural to consider them, so that's why we don't consider them. In particular, you can't do a random walk starting from them. Okay, so let's go back to the situation where we have an arbitrary initial vertex u0, and we imagine doing a t-step random walk from it, where we choose a random neighbor at each step. Now we can ask, what about the distribution of v here? So we don't necessarily know it's the stationary distribution pi, but you may imagine that if you walk for a really long time, perhaps you will start to end up or collect up at the vertices that have the higher degrees. Or in the case of a regular graph where all the vertices have the same degree, you might imagine that after a long walk, you're almost equally likely to be anywhere. Okay, so the question we want to ask ourselves is, as this parameter t, the walk length, goes to infinity, does the distribution of v tend, in some sense, to the invariant distribution pi? Now, there's a couple of edge cases or kind of freak cases where this doesn't happen. You might imagine how it might not happen. One way it could not happen is if G is a disconnected graph. So let me imagine a picture of this. Let's say you have a graph here, G, and it happens to be disconnected. So it has one connected component here, another connected component here. And let's imagine that nevertheless the graph is regular. Maybe every vertex has degree 3, but there's 2 parts to it, and there's no edges between these 2 parts. So then this invariant distribution pi would be the uniform distribution. But you can see, of course, if you start u0 in some arbitrary vertex here, let's make this u0, and you start doing a random walk, you'll always be on, in this case, the left part of the graph. And therefore, no matter how long you walk for, there's no chance that your final position is close in distribution to the invariant distribution pi, which is the uniform distribution. You don't have a chance for v to be uniform on all the graph. It'll actually probably end up being uniform on just this part of the graph in which you started. But in general, it has no chance to be uniform on the whole graph. Notice, on the other hand, though, that if u0, the initial point, is itself chosen from pi, then it has a 50% chance, if these are equal sized parts, of starting on the left side, a 50% chance starting on the right side. And so it is true, actually, in that case, that your final vertex is equally likely to be any of the vertices. But yes, in general, if you have a disconnected graph, this hope, suggested by the question, has a negative answer. There's one more annoying case where this hope fails to happen, and that's if G is bipartite. And in this case, the hope sort of fails to happen for, again, a bit of a silly reason, some kind of odd even issue with T. So if you have a bipartite graph G, it has some vertices here on the left-hand side, some vertices here on the right-hand side, and a bipartite graph has the property that all the edges go back and forth between the 2 parts. They'll go from the left vertex to a right vertex. And again, you can imagine the graph is regular if you want, so that the invariant distribution is the uniform distribution on all vertices. But now you can see, let's say you start at some fixed vertex u0, and maybe it's on the left. Well, you see that if t is odd, then your final vertex will always be on the right. Whereas if t is even, your final vertex will always be on the left. So it is true, if t is a super large odd number, that your final vertex will probably be pretty close to uniformly random among the vertices on the right. But that's not uniformly random on all vertices, which is the stationary distribution pi. And similarly, if t is an enormous even number, the final vertex will have a distribution which is probably going to be close to uniformly distributed on the left vertices, but that's not close to being uniformly distributed on all vertices. So these are 2 annoying cases in which this thing you might imagine, that doing a long random walk eventually leads you to the invariant distribution. 2 cases where this fails. But what's very nice is these are the only 2 things that can go wrong. So let me finally say, otherwise, the answer to this question is yes. As long as you have a connected graph and it's not bipartite, then no matter where you start a random walk, if you walk for a really long time, and we'll start to get quantitative about this later, but if you walk for a really long time, then in the limit, the distribution of where your vertex is after a large t number of steps is exactly the invariant distribution. Okay, so that's another nice property of the invariant distribution. It's sort of the limiting distribution as long as your graph is connected and not bipartite. Okay, but in CS theory, we're not just interested in the limit as t goes to infinity. We always want to know quantitative bounds. Okay, and so the second question we might ask here is, when the answer is yes, you have a connected non-bipartite graph, how fast? How many steps do you need? How big should t be if you want to get epsilon close, in some sense, to the limiting invariant distribution pi? And what's interesting, and this is why we're going to start to get into spectral graph theory and linear algebra and eigenvalues, what's interesting is that these spectral eigenvalue considerations exactly enter into the picture when answering this question. So the answer to this question really has to do with spectral or eigenvalue considerations. And let me give you a taste of why that is. So let's think of an example. Let's imagine you have a graph G, and imagine that it's almost a bipartite graph. So it has a big blob of vertices. Oh, sorry. Imagine that it's almost a disconnected graph. I should have said disconnected. So it has a big blob of vertices on the left and a big blob of vertices on the right. And there's plenty of edges inside each of these blobs. But there's only very few edges that go between the blobs. Maybe just a couple of edges that go between the blobs. And imagine again that this graph happens to be regular, so the limiting distribution is the uniform distribution, just to keep things simple. Now, this is a situation, and imagine the two blobs are of equal number of vertices as well. This is a situation where if you call this set of vertices S, the left blob, one part of a partition or one part of a cut, then these few edges that go from S to S complement, well, this is really a tiny cut, as it said. Okay, there's very few edges here on the boundary of S. And intuitively, that's going to block the random walk from getting to the limiting uniform distribution on all vertices in a short amount of time. You see, if you started at some vertex on the U0 on the left-hand side, and you walk around for a while, you only have rare chances to get over to the other side, S bar. Only when you happen to get to one of these, in this picture, two vertices that has a chance of crossing to the other side, can you get to the other side? And maybe if the degree is 10 or something, you might only have a 10% chance of even crossing to the other side, even when you hit these vertices. Okay, so somehow the lack of edges on the boundary of S is going to be a barrier to this random walk mixing or getting to its limiting distribution quickly. And of course, if there are no edges on the boundary, this is the disconnected case where it'll never get to the invariant distribution. And in the previous part of the lecture, we talked about the fraction of edges on the boundary of a set S, and we saw that it was exactly equal to this quadratic form, script E, applied to the function f, which is the indicator of the subset S. And it's a general phenomenon that if you have some set S where this quantity is quote-unquote small, and I'll again be vague now, and we'll make things more precise later, then that's going to be a barrier to having fast mixing time or fast convergence to the limiting distribution. And conversely, what we're going to eventually see by studying ultimately eigenvalues of the graph, that fast convergence, the property that the random walk from any starting point quickly gets to the stationary invariant distribution, is going to be equivalent to this quantity, the quadratic form of f, never being small. Okay, this thing being not small for all f. So I put all these things in quotation marks because I'm still being a bit vague about what does it mean, small or large. But as we'll see, this is exactly going to characterize when you have fast mixing in a graph, the property that this quadratic form of f is never small.